lousy chalk. BRB. Now, back in the year 2000, Bay, I'm not sure exactly who Bay is, but important scientific computing people chose the top 10 algorithms in scientific computing from the 20th century. And one of the 10 was not really a particular algorithm by itself, but really more like general approach in numerical linear algebra of matrix factorization or matrix decomposition, and relying on matrix factorization for a variety of problems, including AX equals B that we're dealing with, really significantly changed the development of algorithms, really helped move it forward. So we call it the decompositional approach to matrix computations was named one of the top 10. And this is our first taste of it right here. We talked about the singular value decomposition. That is another matrix factorization. We just don't know how to compute that one yet. I won't get around to that till the end. Here we're going to learn how we actually can compute a certain matrix factorization that's advantageous for solving AX equals B. So what we dealt with last time is basically a recap of what you'll learn in your first linear algebra course for solving AX equals B. That you're using Gaussian elimination, so row operations of a form row I is equal to itself minus a multiplier, Mij, times row j. So we all have that form for the purpose of making A equal to an upper triangular matrix that we call U. And then the vector B becomes a modified vector Y because you have to apply the same row operations to it. And also 2/3 n cubed floating point operations, and I forgot to give the abbreviation for floating point operations because that's a mouthful. Flops. So, in fact, MATLAB used to have a command called flops, and if you typed it in, it would just tell you how many floating point operations you've had MATLAB perform during that session. And sometimes we would get cute with it because if you hadn't done anything yet and you typed flops, it would say, spelled out, no flops. Or if you had to do one operation, like 2 + 3, it would spell it out, a single flop. And if I was really doing stuff, I had doing a lot of computation, and I typed flops, and it would have like a zillion, literally billions of operations. Like, wow, I've been really productive today. And one time, I had my class do an assignment of writing code to compute eigenvalues. And so when I implemented it myself, I want to try to match what MATLAB does with its I command. And I never got mine to be quite as efficient as theirs, but I came pretty close. So I was pretty proud of that. But at some point, due to various changes in the foundation of MATLAB, they got rid of the flops command. I was so disappointed. I'm sure many of our MATLAB users were too. But so it's one of those relics of the past. So that's how expensive Gaussian elimination is. We don't like algorithms that take a cubic amount of time. Unfortunately, we're going to see a lot of them. And then once you have this upper triangular system, ux is equal to y, we go ahead and solve that using back substitution. And that costs only n squared flops. And so I'm highlighting this because that difference in order of magnitude between the two processes is going to turn out to be important for us later. Okay. Because what you learn in your first linear algebra course is working with augmented matrix. You put A and B together, you do all the row operations on them together. But that's not really all that practical to do it that way. You want to keep what you do with A separate from what you do with B, because there are many cases in real applications where you have to solve systems with the same matrix and different right-hand sides. And that's going to be made clear today how we handle that. Well, in fact, I should have done this last time. Here's an example of a situation. So you're solving many problems in the form ax equals b. Same A and many B's. And it comes from differential equations. So let's make one up. Solve du dt is equal to, make a heat equation, K times second derivative with respect to x, or uxx. Now, I suppose we're doing this on some interval. I'll just make one up, x between 0 and 1. And I'll throw in some boundary conditions. These are called Dirchleigh boundary conditions. I'm specifying the value of the solution at the boundary points, and I'm going to say it's 0. And then initial condition. Okay. Hopefully I don't give anyone in this class hives from memories of a certain finite elements class, but okay. But we're not doing finite elements. We're doing finite difference. So after discretization in both space and time, the system of equations we need to solve is ujn plus 1 minus ujn over delta t. So this approximates du dt is equal to k, and then we need second derivative with respect to x. And what I'm doing is I'm evaluating the spatial derivative, so uxx. I'm evaluating it at time n plus 1. Instead of time n. Because if I evaluate at time n, that's called an explicit method. If it's time n plus 1, that's an implicit method. So that gives you a flashback too, I guess. Yeah. More so for you, because we're just doing this on your comprehensive exam. Okay. For j equals up to n. So capital N is a certain number of grid points that are equally spaced. And for cases where we end up needing boundary values, like if we go off the edge, well, those values are 0. So what we have here is, this is how each individual equation is written out, but we want to describe this in matrix vector form. We want an ax equals b problem. So I could instead say that A un plus 1 is equal to un. So this is our unknown, like our x, and this is our b. And I can describe a matrix A. A is equal to identity minus delta t times a matrix which I'll call capital D. And capital D is our second derivative operator. Well, I'll throw in the k also. So k, actually I'm not going to do that. I should put the k in here. Okay, so D is for second derivative. So we have 1 over delta x squared. And this is a tridiagonal matrix that has -2's on a diagonal, 1's above and below. Okay. Now, this matrix is tridiagonal because we're describing row J here. And we only use elements for indices J, J plus 1, and J minus 1. Only 3 elements, so that's why we only have 3 diagonals occupied here. So the way to get from this to this is if I multiply both sides by delta t, and then I move ujn to the other side, and I move all of this to the other side, okay. Then I end up with this system here. So now, for time stepping purposes, what I do is I solve this repeatedly for n equals 0, 1, 2, and so forth, where u0 is some vector f that comes from my initial condition. So I have to solve this system a gazillion times, and a never changes. Now, if the coefficient, like if it's k, changed with time, then yeah, it would change. But in this example, it doesn't. And every time I compute a new solution, that becomes the b for the next time step. So, so for implicit methods for solving certain differential equations, that's how these kind of systems come up.
The capital N at the end of J equals 1 to N, that's different than lowercase n, right?
Yes.
Okay.
Yeah, so N is equal to the number of points in the spatial grid. Yeah, okay. Yeah, okay. All right. And totally didn't mean to cover that, but okay. But yeah, I wanted to make it a little more concrete, like why we would do something like that. Okay. So, so the thing is, what we want to do is we want to reduce A to upper triangular form at the beginning before we do any time stepping. And then we don't have, and we have our initial data to apply row operations to also. But then after we perform one time step, like we get U1, and then we want to put that over here to compute U2, we don't want to do Gaussian elimination again with an augmented matrix A and U1 because we've already done all this to A. So what we should do is, all right, so I'll write out how we want to view this whole process differently for the sake of efficiency. So instead of following, Gaussian elimination on A and then U0, then you solve for U1, and I'm going to tally the number of operations, 2/3 n cubed, n squared. And then Gaussian elimination again on A U1 that costs another 2/3 n cubed. And then you solve the resulting upper triangular system, which is the same upper triangular system with a different right-hand side, to solve for U2, it's cost n squared. We keep incurring this n cubed cost every single time step. So instead of doing that, which is dumb, we do this instead. We reduce A to upper triangular form once, and that's still going to cost 2/3 n cubed. And then we save, in some way, a record of the row operations that were actually performed in order to do that. So that's just a storage that happens during Gauss elimination. And then we apply the row operations to only U0. Well, here you're applying row operations not to a whole matrix, but to only a vector. So that takes one order of magnitude operations left. It'll take n squared operations. And then you solve for U1, which is also n squared. That's no different than this. Then we apply the row operations again to U1 as the n squared cost, and then solve for U2 n squared. So the heavy cost is incurred only once, and then we do cheap things from that point on. So what is a practical way to save pertinent information about these row operations that you've been doing, that you do on A at the start? So the key lies in this observation. So for row operation, on A of this form that I wrote down earlier, rho I is equal to itself minus a multiplier times rho J is equivalent to this matrix product. A is equal to A multiplied on the left by a matrix that I'll refer to as capital Mij, and it has this form. Mij is equal to essentially the identity matrix, except in row I, column J, so in this spot, we have minus the multiplier, little Mij. And that's it. Everything else, all the blank space, is 0. So this is a particularly easy matrix to work with. So now I need to tell you a little something about what kind of matrix it is and what properties it has that are going to be very helpful to us. Okay. So capital Mij is now it's lower triangular. You can tell that just by looking. Everything above the diagonal is 0. But there's something more. We can actually call it not just lower triangular, it is unit lower triangular. And what that means is it is lower triangular and it has only once on the diagonal. So I have a shorthand for that too, because I don't like writing out lower triangular. I definitely don't want to write out unit lower triangular. So my shorthand for that is the lower triangle symbol, and I put a 1 above it. So that means unit, lower triangular. And We could do the same for unit upper triangular, but we're not going to use matrices like that. Okay. Now, I should mention terminology-wise, capital Mij is known as an elementary row matrix. So in other words, an elementary row matrix is any matrix that, when multiplying on the left, performs an elementary row operation, any of the row operations, whether it's adding a multiple of a row to another row, or interchanging rows, or also multiplying a row by number. And in fact, the way you get an elementary row matrix from an elementary row operation is very easy. Is you apply the row operation to the identity matrix. So in fact, you can see if you took row J of identity and subtracted from, and multiplied by a multiplier and subtracted it from row I of identity, capital Mij is exactly what you would get. Okay. All right. Now, so one thing that is convenient is a matrix like this is particularly easy to compute the inverse. So Mij inverse is almost exactly the same as Mij. It's just that in, again, row I, column J, you have the multiplier again, but without the minus sign. So the inverse of this unit lower triangular matrix is this unit lower triangular matrix. So in fact, some properties of unit lower triangular matrices in general. So first of all, okay. Well, in fact, I'll talk about not just unit lower triangular, but lower and upper triangular. If you multiply two lower triangular matrices, product is lower triangular. Same with upper triangular, which you can tell by transposing. Upper times upper equals upper. Also, unit lower triangular matrices. If you multiply them together, that also is preserved. Product is a unit lower triangular matrix. So that's going to help us later on. Also, inverting preserves triangularity. So the inverse of a lower triangular matrix is a lower triangular matrix. Same is true if it's a unit. Also, the inverse of an upper triangular matrix is an upper triangular matrix. So inverting and multiplying preserves triangularity. It also preserves unitness, if you have that. Okay. Now, of course, I'm going to show you what happens matrix multiplication-wise if you are performing only one row operation. But now, what happens if you're performing many row operations? What does that look like? It's from a matrix multiplication point of view. Just make sure I don't miss anything in my notes. Okay. All right. you can have a unit upper triangular, and the similar properties would apply. We just won't be using them.
At all.
Yeah, we're biased. Okay. Now, I'm going to define A1, solution 1 to just be the original A for Gaussian elimination. And then, okay. And then I'll define recurrence. AK plus 1 is equal to MK AK for K equals 1, 2, and so forth. So that's going to be the matrix obtained by row operations to eliminate any subdiagonal entries in column K. So actually this would be K1 to up to n minus 1. So in other words, I'm breaking a Gaussian elimination process down into stages, one stage for each column. So A1 is your original, so then M1 works on A1 to eliminate entries in column 1. That produces A2. Then you feed A2 in, you apply row operations on that to eliminate entries in column 2 to get A3, and so on. And finally, AN, that's the final output of Gauss elimination, is your upper triangular matrix U. All right. So now I can describe each of these M's. So MK is a unit lower triangular matrix. Well, actually, I want to describe it in terms of what I had before. So it would be the product of these elementary row matrices, starting with K plus 1K. Wait, I need to do this in the opposite order. Starting from MK plus 1K, that's the first entry that gets eliminated. Then K plus 2K, K plus 3K, and so on, until the very last row operation that's working on the entry in row N, column K. And I have to stack them up to the left because we're doing row operations. We're only multiplying by things on the left. Now, each one of these is one of those unit lower triangular matrices over there that has its identity except for this single minus multiplier somewhere in the lower triangle. So it turns out when you multiply all of these together, the product is very convenient. It's also a unit lower triangular matrix, but the properties gave you earlier. And in column K, these negative multipliers just overlay each other. So we have minus M K plus 1K, minus M K plus 2K, and so forth, all the way down to minus M N K. So it's very easy to see how. So in fact, it's almost like if you took those multiplier matrices all from the same column and you just laid them on top of one each other, like through see-through paper or something, you get exactly that. That'd be kind of fun, actually. Okay. And another nice thing, and this is something that you might try, like convincing yourself of by trying it on a simple example to see why the matrix product of all of these works out so nicely. So what else is convenient is the inverse it's going to work out just as easily too. It's just going to be the same thing without the minus signs. Okay. So if I define LK to be MK inverse, then I'll just write down LK is 1's in the diagonal, and then plus MK plus 1K, K plus 2, K, all the way down to MN. Okay. So what happens during Gaussian elimination? Assuming that there's no need to do row interchanges, and we'll deal with that next week. Okay. So you start with A, and then you apply M1 to it on the left to eliminate elements in the first column. And this gives you A2, because A1 is A itself. And then you work on the second column, M2. This gives you A3. And you keep going. So finally you work on the second last column, column N minus 1. And eliminate the one entry below the diagonal there. And the result of this is your upper triangular matrix U. Now, what we'll do is, we've seen what the inverses of these look like, so let's just move everything to the other side. So, so I'm going to multiply by all the inverses on the left. So when I'm canceling all these matrices and moving them to the other side, one thing about it's kind of weird. You see a lot of times in math lectures or presentations where if someone's doing manipulations like this, and I want to, say, move these to the other side, and what a lot of people will say in this situation is they'll say, okay, I'll move this guy to the other side, and this guy, and this guy. And it's almost sexist in a way, because can you imagine if I, because can you imagine if I'm presenting this, like I have been doing, and I say, and now I'll move this girl to the other side, this girl, everybody's brain would just go, like, what? So that's just an interesting sociological commentary there, but yeah. But because I see that happen all the time, it's like, well, what if it all flipped around? Okay. Anyhow,
There's like different things that we put genders on, like cars. Like you always say like.
yeah, cars.
Are always like she's.
Yeah, vehicles of any kind.
Yeah.
Boats, planes.
Oh, boats too.
No, definitely boats. Yeah.
Definitely boats, yeah.
Computers.
Oh yeah.
I thought about that one, but okay.
You can work. You can
Not
do it. You
computer.
can do it.
Okay, yeah.
So.
Yeah, so weird how it is. So yeah.
Well, in French, everything has a gender. So
And then Spanish too. Yeah.
Spanish, everything has. Does anybody speak Spanish?
Yeah.
Yeah, Spanish in high school.
Everything has
Yeah.
a gender.
El en la.
Oh, okay.
El niño, las niñas.
And you have to do it. Okay. I took French, so.
Okay, yeah.
We're like the only language that doesn't do it, but then we do it in different and weird ways.
Yeah, well, because all that comes from Latin, which imposed genders, and
Who decided the gender thing? Like, I
It was-
think that's gonna be a female.
yeah, because for things that like inanimate objects, it's like why, and,
Doesn't some of it, like I know in French, has to do with like vowels too? Like if it starts with a vowel, then it kind of sounds, is it like that?
It's ending in vowels.
Oh, okay.
Yeah, and that dates
Both
back.
in French and, because
And that dates back to Latin also, where they have different endings, like O is a masculine ending and A is a feminine ending. But Latin actually had two different words for man. One for man as opposed to an animal, and the other for man as opposed to a woman. They're two entirely different words. So,
in Japanese too, feminine verbs and masculine verbs.
Oh, okay.
Adjectives.
Like what?
I mean, if I say it, you won't understand it, but like, there are two different.
I can tell the difference. I can probably tell the difference.
All right.
Let's say like, so for the adjective black, right, color, if you say kalo, that means for a male, and if you say kali, that's for a female.
Like if you're describing something that is.
Yeah, you use a specific one.
And if you say the wrong one, like do people kind of look at you weird, like funny?
I mean,
They would be able to understand you, but it's just like saying like
yeah, it's just weird.
a octopus or something, like us not using the right.
Yeah.
How did we get like way off topic? Oh, there you said you started it.
Yeah, I know. Yeah.
Okay, alright, cool.
Okay.
Cool. Languages.
Yep.
Interesting.
Okay. So that's why I commented, I'm going to move this matrix over to the other side.
Okay, this guy. You could just start saying this gal. And
Yeah.
we'll just.
Yeah. Well, apparently some people outside of USM watch these things.
Really?
Yeah, like one asked somebody, I have no idea who he is, like asked a question
Nice.
on YouTube.
I should start sharing you. I mean, nobody follows me, but you're getting out there.
So this is the first one to go. So n minus 1. Inverse. Whoops. Okay. So n minus 1 inverse. And followed by n minus 2 inverse. And so forth. All the way up to the last ones. M2 inverse and then M1 inverse. But I've already defined what the inverses are. These are these L's. So I have L n minus 1, L n minus 2, going from right to left, L2, L1 times U. Now, the M's are unit lower triangular. The L's are inverses of M, so those are also unit lower triangular. They're all multiplied together, so the product is unit lower triangular. So I'm going to take all of these and call them L. So A is factored into a product L times U, where L is unit lower triangular, U is upper triangular. And here's the best part. We know exactly what L is. So it has all the ones in the diagonal, zeros above, and then what we get are, so just as in one of these L's, we had all the multipliers in a column, the products of these work out nicely, so we just have all the multipliers stacked together. So every single multiplier is in L. Okay. So that meets the goal we had up front of if we're performing Gaussian elimination only on A, we don't have a right-hand side B at all yet. But we want to keep a record of the row operations that we performed so that we can apply them later to whatever right-hand side vector we have. There is our record. It's in L. So what we do is, as we're going through Gaussian elimination, and what's happening is we keep updating. We're interested in updating like what will be the upper triangular portion of A that we're going to use later in back substitution. As we go through this process, we're working on this upper triangular part, we can just store the multipliers in the lower triangular part. Because that's the part that in A is going to become 0 anyway. But why store a bunch of zeros? Because that's kind of wasteful. So now all of our real estate, in A, can be used. So the result of Gaussian elimination goes in the upper triangle. The multipliers go in the lower triangle. Right, so this is called the LU factorization of A. Okay. So this is what Gaussian elimination produces. This is never thought of that way in a typical first linear algebra course. But what happens is, because if you know what the multiplier is, and you also have, based on the position in the matrix you put it in, because multiplier ij goes in row I, column j, then you can reconstruct from that exactly what the row operations are you need to perform, and you can then use that to apply those same row operations to any vector later on. All right. So now you've learned how to factor a matrix, which I think is much more interesting than factoring polynomials. Although some algebraics might disagree with me, but whatever. Okay. So now that we know how to get an LU factorization, and all it is just another way of looking at the Gaussian elimination process you already know about, how do we use this to solve AX equals B given that we want to work on A and B separately, just because B could be changing while A is not. So solving AX equals B using LU. So first I'll derive it and I can lay it out as step by step. So if AX equals B, then I will place A with LU. So LUX is equal to B. So here's what we can do. I'm going to take this vector U times X, which at this point is unknown because X we don't know. And I'm going to call that Y. So now we have L times Y must be equal to B. Well, after we get the LU decomposition or factorization, we have all the information we need. We just need to solve for Y. Now, instead of solving AX equals B, we're solving this system, LY equals B. But L is a unit lower triangular matrix. So this could be solved using what is called forward substitution, as opposed to back substitution that you use with the upper triangular matrix. Okay, so I did all that, Okay. So now I'll write out the algorithm for forward substitution, and then I'll summarize the entire process. So forward substitution, solve Ly is equal to B. Forward substitution is a lower triangular matrix, so the first equation is a trivial one to solve, and you work your way down to lower equations. So you start your loop, and from 1, 2, all the way up to n. And you set your unknown, yi, originally equal to bi, And the thing is, if you compare this algorithm to the back substitution algorithm from last time, Tuesday. Yes, I really did forget what day it is for a moment there. You're going to see a lot of similarities. So now what you do is you have a number loop for j equals 1 to up to I minus 1. Because with an upper triangular matrix, you want all the columns after I. For lower triangular, you want all the columns before I. And just like in back substitution, you're subtracting off terms. So you'll recognize this exact same step in back substitution. And that's this. Now, one key difference is in back substitution, after this loop, you were dividing by a diagonal entry. But how come I don't need to do that here?
It's all one.
Yeah, we're all one. So this only works for a unit lower triangular matrix. If you wanted forward substitution for a general lower triangular matrix, you just have to modify this to divide by LII after that inner loop.
I might have missed it. Did you say why we have to use forward substitution over backward for this?
Oh, because lower triangular. So back substitution is only for upper triangular.
Yeah, see, I missed that part yesterday.
Oh, right. Okay. Well, I'm going to summarize everything.
Okay, so since
right
it's
now.
lower, you use forward.
Yeah.
Because in backwards, you have your last variable first. Like in an upper triangular matrix, you can see your last variable first. Because it's, like if you picture an upper, right?
Yeah. Yeah. That's what. Yeah.
You're
Because.
moving backwards, but lower triangular, you have your first variable.
Right.
Yeah, like if you think of it as a system of equations, right?
Yeah, and in which equation is easy to solve first.
Right.
That was good.
I took real good notes for you. I did.
You're welcome.
Okay. So now I can describe the whole process along with how many operations you have at roughly each stage. Okay. Okay. Oh, wow. Didn't realize only 18 minutes left. Sorry. That's fine. I will not fall behind.
Won't take long to summarize, right?
Oh, no, and I have a couple other things to do, but that's easy. Okay. So the whole process is first, okay, so AX equals B. Okay. So first thing you do, Gaussian elimination. And that produces the LU factorization. A is equal to L times U. And as mentioned before, it takes 2/3 n cubed, floating point operations roughly. Okay, so that's the expensive part. Then you use forward substitution to solve Ly is equal to B, and that takes m squared operations. Now I should mention what this does is that is as the effect of applying the row operations to B. So the same ones you applied to A to get your upper triangular matrix U are now applied here. And you can see why, because Y is equal to L inverse B. Well, your U, that's the result of Gauss elimination, is equal to L inverse A. So applying the row operations means multiplying by L inverse, or mathematically equivalent, but you would never construct L inverse, you would just perform the row operations. Okay. So when you were using the augmented matrix, you slapped A and B together and did your row operations, you were doing both of these at once. So after you were finished, you had U, so in other words, A, B, as augmented matrix, under Gaussian elimination and as the effect of multiplying by L inverse gives you your U on the left side, and then you have your Y in the last column, because you're applying this row operations to that too. Okay. All right. So unlike in your first linear algebra course, we're now treating these things separately. Last thing is we want x. So you use back substitution. To solve, because earlier it defined y to be equal to ux. Well, now we know y. So now you can, and we have u, so we can just obtain x by solving S system. And this costs also n squared operations. Okay. So now, if B changes, but A doesn't, then all you have to do is steps 2 and 3. Because you could use the same L and U as before. So you'll just repeat the forward substitution and back substitution. Okay. All right, so questions about that? Okay. I'm doing on time here. 6:11. Okay. Well, this part, I have an example here in the notes. I'm not going to do it now. I might have Amber do it next week. Okay. Let's see. Okay. So one thing I definitely want to cover is I said this earlier, but I want it in your notes. What you do is, during Gaussian elimination, what you should do is store the multiplier, little Mij, in the IJ entry of A. So you keep working on A to reduce it to upper triangular form. But as you're computing multipliers for that task, that's where you put them. So A gets overwritten with this matrix that, like, from a diagonal and above, that is U. And then you have all of your multipliers stored in here. So in other words, the interesting part of L is stored below U, because that part's being cleared out and zeroed out anyway. At least you have something useful to put there. Okay, so just for efficiency's sake, you don't want a function in MATLAB that computes L and U and stores them in separate matrices, because then you're wasting space of all the zeros. Okay, that's one important thing. Then I also want to talk about existence and uniqueness of the LU factorization. Okay. So first of all, not every invertible matrix A has an LU factorization. So it's not always possible to compute. And I can give a very simple example of a matrix that does not have a LU factorization. Any matrix that has a 0 in its 1-1 position does not have an LU factorization. Because what would happen is you divide by 0 right away, because you're going to use this as a denominator in all your multipliers for a first column. Now, it's easy to get around. You do row interchanges. We haven't incorporated row interchanges into our process just yet, so that's something that will be done next week. So you have to do a modification of its factorization. So it's not A equals LU. It's some modification of A by row interchanges that has an LU factorization. So I can tell you in general when the decomposition exists. So, and it's not an easy condition to check, but at least we know what it is. So, so I can find a sequence of matrices. AK will be, using MATLAB notation, kind of, rows and columns 1 through K. So we take the upper left K by K block. So in other words, in my matrix, the 1-1 entry is A1. Then the upper 2 by 2 block is A2, then A3, and then the entire matrix is AN. And these are called the leading principal submatrices of A. All right, so this is going to help me state the condition for existence. All right. So, this factorization exists if and only if the principal minors, which are defined to be the determinants of all these leading principal submatrices, are all non-zero. So in other words, all these leading principal submatrices have to be non-singular for this to work. So A1 is just the 1-1 entry, so that has to be non-zero. And actually, it's actually kind of fun to check. If this is non-zero, but then I wanted to check on what would it take to make sure that this diagonal entry was non-zero. Like after you work on the first column, then you want to make sure that your new diagonal entry in the second column is non-zero. Sure enough, that would only be non-zero if the determinant of the original 2 by 2 block was non-zero. You can actually figure out how the elimination goes for that second row. So that's the approach that you use to try to prove that LU exists if and only if all these principal minors are non-zero. Okay. And since I still have time, I can also establish uniqueness. Okay, so if LU exists, it is unique. And I can easily show this. So let's suppose that two LU factorizations exist. So L1U1 and L2U2. Now, A is invertible, so that means that all of these factors are also invertible. Well, the L's are automatically invertible because it's a unit lower triangular matrix. Its diagonal entries are all ones. Because A is invertible and L is invertible, U also must be invertible. So I can use the fact that these guys are invertible to move things around the other side. So I can say L2 inverse L1 is equal to U2 U1 inverse. Now, what kind of matrix do we have, like structure-wise, on the left? Yeah, like in terms of properties of certain triangular matrices and all that.
They would both be lower.
Yeah, L2 and L1 are both lower, but so then the product as a whole.
Lower.
Yes, and what else can we say about it? So
It's a unit if L1 and L2 are unit.
L1 and L2 are unit because that's an LU decomposition.
Oh, so
Yeah. And what about the right side?
It's upper.
Yeah. Well, when you have a
it's not unit.
No, it's not.
no, it's not unit.
Right, it's just upper.
Yeah. So
Excuse me, so how do you say that it's not union? The right one?
oh well, because U1 and U2 are general, not unit upper
Okay,
triangular. Yeah. Okay. Now, well, the thing is, if you have an upper triangular matrix equal to a lower triangular matrix, then what must be true of the matrix in general? No,
Identity?
Oh, never mind.
that's coming, but yeah, it's diagonal.
Oh,
Yeah, because the only entries that are non-zero in both sides are the diagonal. So it must have diagonal, but all the diagonal entries are 1. So it's a unit diagonal matrix, which is the same as identity. Yeah, so what that means though is that both of these are identity. That means that L1 equals L2. So if I rearrange based on this, and then U1 equals U2. Yeah. And thus we have uniqueness. Okay. Okay. Very last thing. Even though we don't really deal with determinants very much, it turns out that the LU decomposition gives us a convenient way to compute determinants. And in far less time, it is using the definition that you learned in a regular linear algebra course. So, A is equal to LU, well, the determinant of a product is a product of the determinants. But also, the determinant of a triangular matrix is just the product of all the diagonal entries. So we have this for determinant of L, and then we have this product for determinant of U. Okay. So, but what are these entries for L? What are they equal to? Yeah, we're all 1. So it's just the product of the diagonal entries of U. So after you perform Gaussian elimination, then you just multiply the diagonal entries in the result, and that's the determinant. So this is accomplished in a grand total of order n cubed operations, well, 2/3 n cubed, because it's the cost of Gaussian elimination, versus n factorial from the definition of determinant, from theoretical linear algebra. So that's a huge cost savings. Okay. And this also stems from the fact that if you multiply, if you add a multiple of one row to another row, that doesn't change the determinant. So that's another reason why the determinant of A is equal to the determinant of U, because that's how you get U, by performing those kind of row operations. Okay. All right. So, all right, I'm done.